Hello, in this video we're going to look at the probability of being in the fourth quadrant given that our random variable is a standard bivariate normal random variable. And really I want to be able to point back to this video in some other videos that I'm doing. But for this video I'm going to suggest two background videos. Background video 1, which is integrating a bivariate normal distribution, and that's there we show that integrating a bivariate normal distribution integrates to 1, which it should. And then background video 2 is the probability of being in the first quadrant for a standard bivariate normal random variable. And so here we have a vector x and y, which is multivariate normal, mean 0, and variance covariance matrix this. So the variances are 1, so the off diagonals are the correlation. In this video, we look at being in the fourth quadrant, which means x is positive and y is negative. Of course, in BV2, we looked at or calculated the probability when in the first quadrant, so x is greater than 0 and y is greater than 0. So this is going to be similar, but different probability. Okay, so from background video 1, we showed here that we could split that bivariate normal density into this piece, sort of the product of these, individual pieces. So then when we calculate this probability, which means, so we're going to integrate y first. So y goes from 0 to negative infinity, and x goes from 0 to positive infinity. And we do a variable transformation. So this 1 minus rho squared, we pull into here under the squared term, but we have to square root it. So when we bring it back out from the squared, we get this. So we let z be this, which is sort of this piece here. And let's look at what that does to our region. Okay, and so for this case, we're going to assume that rho or our correlation is positive. And then I'll point out the pieces where, actually the result's the same, or the formula we get at the end, but it's a little different. And I'll show you. So here, this is our transformation. And so here, originally x and y, we want to be in this fourth quadrant. This is our variable, and so edges are mapped to edges. So this first edge is mapped to this diagonal. So this is when y is 0. So if you put in y's 0, and then we get this slope. So x, of course, goes from 0 to infinity, and z is this line. And since p is positive, or rho is positive, it's like this. Now, if rho were negative, it would actually go like this, okay? But in side 2 is when x is 0, so y goes, or z goes from 0 to infinity. So it's actually mapped to the same thing. And the region is here. Now when it's negative, it goes up like this, and the region is a little bit bigger. So we back solve for y, take the derivatives with y and z, we get this. Now we plug this into our density here, and we get this. So now, our limits of integration, when you plug in 0 and infinity, you're going from here to negative infinity, and here, it's from 0 to infinity. So these are the limits of integration, but this is not a fun thing to integrate. So we're going to transform it to polar coordinates. So we let x be this and y be this. And by BV2, we showed that the Jacobian of this transformation is r. And so the absolute value of the Jacobian is r. It's the radius. So now let's plug in this information to our density, and we get this. And you can look at BV2 for a little more background on this if you want. Now, again, this is still sort of ugly to integrate. So what we do is we do a u substitution on this exponent, and then du is equal to minus r dr. And then so that r can be brought in here, but we need a minus and a minus to grab that. So then we're left with this piece. And when you plug in 0, you get 0. When you plug in infinity, you get minus infinity because of that minus there. So now to integrate this with respect to u, we just get u back, and then you plug in minus infinity, and that goes to 0, and then it's minus, then you plug in 0 and you get 1, so it's minus a minus, and you just are left with this positive, 1 over 2 pi. Now to integrate this, you bring out the 1 over 2 pi, and it's theta, and then it's evaluated at this, and then minus, plugging in that, and then it can be simplified to this. And what's interesting is when rho is negative, then we go from minus 2 pi to positive arc sine of rho. But when rho is negative, it actually can be brought out here and made positive and negative. So it actually ends up being the exact same integral. Well, anyway, that's all I have for today. Hopefully you enjoyed that. If you did, please like the video, subscribe so you don't miss the next one. Thanks, bye.